Welcome back to the Carnival Tycoon project, lesson 3. Just want to go ahead and review a couple things from lessons 1 and 2. Lesson 1 had to do with an introduction to probability, events, and sample spaces. We then moved on to lesson 2, theoretical versus experimental or empirical probabilities. And now we're moving into lesson 3, which has to do with dependent and independent events. So let's start out, shall we, with some basic definitions of what dependent and independent generally mean. Some basic Webster's dictionary stuff here. Dependent means something that is conditioned or it's determined by something else. So another word we use for that is contingent. So an example of that would be our trip to Michigan Adventure, or Michigan's Adventure, is dependent on the weather. Maybe you've been to Michigan's Adventure before. They don't even open the water park until it gets to be about 70 degrees. So if you plan to make the trip out there, you better be watching the weather. Independent is the exact opposite of that. Independent events are not contingent upon something else for its existence or operation. So an example here might be the voter's opinion was not swayed by anything or anyone. She was a true independent thinker, not influenced by anyone in her family or any of her teachers or anything she hears on the news. She is a true independent thinker. So that's the difference between dependent and independent. Just the definitions of the words, that is. So if we're speaking of dependent versus independent in terms of probability, we've put together a flowchart to help us understand the difference between the two. And if you're ever wondering or having a difficult time determining if an event is dependent or independent, you can go back to this flowchart and check it out. So let's take a look at what it says. And this is on our website for lesson 3. So for dependent versus independent, you first have to ask yourself a question. Is it possible for the event to happen or the events to happen in any order? If that is not possible, then we're definitely talking about dependent events. So let's take event A and event B. If it is not possible for them to happen in any order, for instance, if event A has to happen before event V can happen, well, then it's dependent. B is dependent upon A. You cannot drive a car before you have gasoline. If it is possible for the events to happen in any order, then we have to ask another question, because it's not necessarily independent yet, because the second question we ask is, does one event in any way then affect the outcome of the other event? And if that is true, if by A happening, it changes something about the likelihood of B happening, then it is also dependent. But if when A happens, it has absolutely no effect on B happening, then it is an independent event. So the flowchart is a very good way of following the line of thought and trying to help determine if something is a dependent or an independent event. We have 3 examples we want you to think about right now. One has to do with someone living in Ohio and enjoying the Gemini. Maybe you've been on that roller coaster before. And another one, and the other 2 events both have to do with people fishing. So we're going to go ahead and put those up right now for you to consider. So here is event 1. What is the likelihood that an Ohioan will enjoy the Gemini roller coaster at Cedar Point this summer? The likelihood that an Ohioan, so someone who lives in the state of Ohio, will enjoy the Gemini roller coaster at Cedar Point this summer. What I'd like you to do is I'd like you to go back to the flow chart, and I want you to follow the reasoning of the flow chart to determine if this would fall into dependent or independent events. Go ahead, give it a shot. All right. Did you think about that? The likelihood of an Ohioan enjoying the Gemini roller coaster this summer. Well, let's think about what would have to happen for this to occur. First of all, you would have to be an Ohioan. Then you would have to go to Cedar Point this summer. And then you would have to choose to ride the Gemini before you could make the decision on whether you enjoyed the Gemini. So there are a number of events that would have to occur here. The question is it possible for the events to happen in any order? Well, let's just take two of the events. Riding the Gemini and going to Cedar Point. Could you ride the Gemini without going to Cedar Point? Well, the answer to that is obviously no. There's only one Gemini and it's at Cedar Point. So clearly this is dependent, and many of the events in that string of events are dependent on one another. It is dependent. A lot of people from Michigan, for instance, go down to Cedar Point and enjoy the Gemini. They're not Ohioans. All right. The next one, Event 2. Kiera is a catch and release competitive fisherman. What is the likelihood that she will catch at least one bluegill and one perch on today's fishing excursion on Fawn Lake? Go back into your dependent and independent flowchart and follow your reasoning through this one. Kiera is a catch and release fisherman, competitive fisherman. What is the likelihood that she will catch at least one bluegill and one perch on today's fishing excursion on Fawn Lake? Well, did you figure this one out? All right, Kiera is a competitive fisherman. She's on Fawn Lake, some kind of fishing competition, and what is the likelihood of her catching a bluegill as well as a perch today in the fishing excursion? Well, is it possible for the events to happen in any order? Could she then catch a bluegill and then 5 minutes later catch a perch? Or catch a perch and then 5 minutes later catch a bluegill? That's certainly possible. So far, it's not dependent, it's independent. But we'll see. We have another question to ask. Does one event in any way affect the outcome of the other event? So if Kiera catches a perch, will it affect the likelihood of her catching a bluegill, for instance, or the other way around? Well, there's something unique about what Kiera is doing, and that is she is a catch and release fisherman, which most competitive fishermen are. And once they catch the fish, they measure it and weigh it and throw it back into the lake. So if we started with 1,000 perch and 1,000 bluegill, Kiera catches one bluegill and she throws it back. So after she caught the bluegill, there's still 1,000 bluegill and 1,000 perch in the lake. So does one event in any way affect the likelihood or the outcome of the other event? No, it does not. So this is an independent event. We've got one more. Here it is. Event 3. Bryan is also fishing on Fawn Lake, but for the purpose of catching fish for his family's summer fish fry. What is the likelihood that he will catch at least one bluegill and one perch on today's fishing excursion? Go ahead and look at the flowchart and try to determine if this would fall under the category of dependent or independent events. All right, you probably realize there's something a little bit different about Kiera and Bryan's fishing experience today. Kiera is catching fish and throwing them back and not changing the number of fish in the lake, but Bryan is catching fish and keeping them and throwing them in a bucket so he can fillet them later and fry them up for his family's fish fry. So let's go back to the top for Bryan. Is it possible for the events to happen in any order? Can Bryan catch a perch and then 5 minutes later catch a bluegill? Oh, he certainly could. And could he do the exact opposite? Could he catch a bluegill and then 5 minutes later catch a perch? Absolutely. So far it's a yes. But the next question, does one event in any way affect the outcome of the other event? So if Bryan catches a perch and he throws it in his bucket, and there were 1,000 perch to start with at the beginning of the day, now there's only 99 perch, but there are 1,000 bluegill. So somehow we've changed the ratio of perch to bluegill in the lake. So it does affect the outcome of the next event. So if he caught a perch, then there'd be a less likely of a chance to catch another perch because there's less perch in the lake, and a higher likelihood of catching bluegill the next time around. So does one event in any way affect the outcome of the other event? Yes, it does. Now, in Bryan's case, it doesn't affect it that much, but it does affect it in some way. So this is dependent as opposed to Kiera's independent. This is a great flow chart to go back to if you're having any trouble at all determining the difference between if events are dependent or independent. And we've put this on the lesson plan page for lesson 3. Access at any time. So now we've set the groundwork for dependent and independent events. We're going to write down a few things in our notes. So if you would go ahead and access your notes, these are on the lesson plan page. This is just a continuation of the notes that we've been taking for the first 2 lessons. These are lesson 3 notes. Go ahead and get those out and get ready to go. So here we are with the lesson 3 notes on dependent and independent events. It's actually labeled compound events because compound means more than one thing happening at a time. So that's the first thing we'll write down here. Now, your notes are mostly filled in for you. Mine are pretty much a blank slate. So for Roman numeral 1, compound means dealing with more than one event. More than one event. And for the most part, we'll be dealing with 2 events in this lesson happening at the same time, either dependent or independent of each other. But compound could mean as many events as you want to put in there. Could have 100 events happening. The likelihood of 100 or 1,000 events happening would be compound events too. All right, so with compound events, we have 2 different types, and we've already established the baseline definitions of dependent and independent, but in terms of probability, independent events, and I will not write every single word out because you have those in your notes. This is when one event does not affect the likelihood of the next event occurring. So one event does not, is the key word, affect likelihood of next event. That's not exactly what yours says, but it's pretty much the same thing. All right, so 2 events happening, and one does not affect the likelihood of another. So for dependent events, I'll roll this up just a little bit for you. Again, this is the exact opposite of independent. For dependent events, one event does affect the likelihood of the next event. So for B to happen, A would have to happen if it's dependent, but if it's independent, B could happen whether or not A happened. All right. So we're going to spend a few minutes discussing how to calculate event probabilities, and we're going to start out with independent events. So two events that have honestly nothing to do with each other, or they don't influence each other in any way. So we're going to go ahead and write down our formula for how to, actually our equation for how to solve for independent events. So for independent events, the formula that we will use, the probability of event A and event B happening is equal to the probability of event A multiplied times the probability of event B. So let's take the example of, for number 1 here, the likelihood of getting a prime number when rolling a die and getting heads in if we flip the coin. Both of those events, those compound events happening at the same time, prime number and heads. Well, let's see here what a prime number would be on a die. Remember that prime numbers from mathematics are numbers that can only be divisible by themselves and by 1. So let's see, on a die that would be 1, that would be 3, and that would be 5. So on a die, there are 3 out of 6 of the rolls of the numbers that are actually prime. That's a pretty high percentage. That is 1 out of 2, or we call it 0.5, or 50% chance of getting a prime number when you roll a die. How about heads? This is pretty easy. We did this in lesson 1, maybe even a little bit in lesson 2. Heads, of course, we know there's only 2 options on a coin. So heads is a 1 out of 2 chance, or 0.5 or 50%. I like to write this out in percentages and decimals as well as fractions. It reminds us that you can use those different descriptions at any time when you're calculating probability. So we have to have these 2 events happening at the same time, meaning we have to multiply those together. So the probability of a prime number, it is 3 over 6 multiplied times the probability of heads, 1 out of 2. That will give us, get a little bit crazy here, that will give us 3 out of 12, which is the same as 1 out of 4, which is 0.25 or 25% chance of getting that. All right, that makes a lot of sense. All right, so it's 25% chance by multiplying those 2 numbers together. How about the second one? The second one is a spinner disc. Let's say the spinner disc for number 2. Number 2, the spinner disc has 9 equal pie-shaped sections. And you spin this thing by flicking the little spinner, and it lands on one of the 9. All right, so what's the chance of getting a 5 on that spinner disc? Well, we know we can get a 1, 2, 3, 4, 5, 6, 7, 8, 9, and a 5 is just one of those. So the chance of getting that 5 is 5 out of 9. I'm sorry, it's not 5 out of 9. It is just 1 out of 9. There's only one 5 in the spinner disc. All right, so 1 out of 9 chance of getting a 5. All right, so then, of course, it's tails, for example, too. Tails, we know that is also 1 out of 2. So if we take those 2 and multiply them together, the 1 out of 9 chance multiplied times the 1 out of 2 chance, we will get a 1 out of 18 chance, and this isn't a decimal that we are normally used to seeing. or being able to figure out in our head, it is 0.06 or a 6% chance. So a 6% chance of getting a 5 as well as tails. And our third example would be the spinner disc again, this time giving us odd numbers on the spinner disc. Okay, we've got 1 through 9 on the spinner disc. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Which ones of those are odd? Well, 1 is odd, 3, 5, 7, and 9. That's 1, 2, 3, 4, 5. There's where our 5 out of 9 comes in. So a 5 out of 9 chance of getting an odd number on a spinner disc. All right, and the next one, of course, is heads. So if we get heads, we know heads is a 1 out of 2 or a 0.5 chance. All right, so we just multiply those together like we did before. Our chance of getting an odd number, 5 out of 9 on the on the spinner disc, multiplied times 1 out of 2. That will give us 5/18. And again, not necessarily something that just comes to us on the top of our head, but if we put it in a calculator, 5 divided by 18 is 0.28 or 28% chance of getting those two things to occur at the same time. So as a review for compound events that are independent of one another, they have no effect on each other, all we have to do is multiply the likelihood of one times the likelihood of the other one. And generally we're talking fractions, so that's the easiest way to go about that. Sometimes just you can take the decimals and multiply them too. You get the same thing. But that will give us the likelihood of both of the events happening. All right, so what we're going to do is we're going to go into our probability activities, and we are going to tie this in a little bit to lesson 2, because if you remember in lesson 2, we went about learning about the probabilities that were theoretical versus the probabilities that were empirical or experimental. Because mathematically, we can figure out the probability of something happening, but then when we put it into practice, we know that sometimes we get different numbers from that, or numbers that kind of hover around what our theoretical probability is. So I'm going to take a moment to go into the probability apps and show you just a couple things because we're going to be using the dice roller and the spinner and the coin flipper. So let's go ahead and go to our lesson plan page and open up our probability link. So here we are on our probability learning activities page. I want to take you through a couple things. I want to just review the coin flipper and the dice roller and the spinner. I just want to show you basically how these work because you're going to be doing an activity that takes about 15 minutes that will involve you manipulating these apps. So the first one will be the coin flipper. And just like before, I like to spread out the data tables. How many coins should you flip? Well, you have complete control over that, but we want you to flip 1,000 coins. But I'm just going to throw in a number here, 55 coins. And you hit go, and it gives you the results right here. You can simply look at this and see that when we rolled 55, we got 28 tails and 49 heads. All right, so that would give you the results. There's really no need in the coin flipper to put it into any type of graph or anything like that because the data is just so simple. But in the other ones, I'll go back to the next one, which is the dice roller is a little bit different in that it may be beneficial to you, well, it will be beneficial to you to use some graphing. Let's say we're going to roll 50 dice, and we go ahead and roll them, and we get all this data here. Well, it's hard to extrapolate that data without actually putting it into some kind of graph. Well, CodeApp gives you a really good tool for that. All you got to do is go up here where it says graph, and we're just going to, right now it's just a plot all over the place. We're going to change the y-axis to the number of dice, and the x-axis to the, the x-axis there we go. The x-axis to the value. And what you can see here is you can see that we have a number of 1s, 2s, 3s, 4s, 5s, and 6s. No 0s and 7s. I wonder why that is. All right. You could count these up, but it's a little easier to use if you go over to this tool here, you can group them into bins. And when you do that, you can use the little ruler and give us a count as well as a percentage. So the ruler and the little graph icon here next to the bar graph are super helpful. So now we can see that 9 out of 55 were 6s, 12 out of 55 were 5s, and all the way down to 5 out of 55 were 1s. And our data can be collected that way and analyzed. A lot easier than going through here and counting up all of these numbers. Imagine having 1,000 and having to take all that data out and graph it yourself. So the CodeApp app is really, really great when it comes to that. So let's leave this site and go back to the spinner. The spinner is just a little bit different in that we have to manipulate the spinner a little bit to make it do what we want it to do, which is really nice because it will work for later on in some lessons in the future where we need some specific dollar values, for instance, in this spinner. So we're going to go to this little checkbox here, and we're going to make a custom spinner. And our custom spinner, we want just to go from the numbers 1 through 9. So just like in the example in the notes, the spinner has 9 equal sections, and we'll click OK. So if you look at the spinner now, you can see it's 1 through 9, and it's clearly labeled. So let's go ahead and say we are going to get one result out of like 10 spins, 10 samples. And then we'll just go ahead and start it and let it do its business. 1, 2, 3, 4, and it just spins and records the data as it goes. I'm going to stretch this out just a little bit. So you can see, there we go. We got all the values for our spins. We got a 2, a 6, a 5, a 3, an 8, a 9, a 4, a 3, and 2 7s in a row after that. Now, that's not very much data, but you could just analyze that data just by looking at it. But if we had a lot of data, then of course we could make a graph of it and do similar things that we did to the last one for the dice, for rolling the die. All right, so what we want you to do is we want you to take the what we did in the notes, basically, and we want you to do these same things for that was theoretical probability. We want you to do the same thing for the empirical results that you get using the CodeApp app. So the directions are going to be up on the screen for activity 1. It'll take about 15 minutes to do, and you'll be going back and forth between these three different apps, using them to generate the data that you need to record your actual empirical or experimental probabilities for these things. So the directions will be up on the screen as to how to get the assignment. Remember, all assignments and activities are on the lesson plan page. So you'll find the links for activity 1 on the lesson plan page in all the different formats that you might use or you might need. Good luck. Welcome back from activity 1. Hopefully you learned something, and hopefully you got a little bit more adept at using our CodeApp probability activities applications. How did it turn out? Did your theoretical probabilities from the notes match up closely to your empirical probabilities in activity 1? It's likely that some of them did, and it's likely that some of them did not. And that was one of the things you needed to discuss in the questions as to why that was really the case. All right, right now we're going to move from independent events to dependent events. So if you would, please go ahead and take out your notes that we had started a few minutes ago on dependent and independent events. So remember that dependent events are contingent upon one another. So a dependent event would be, if we would take event A and event B might not even happen if A does not happen. Or B might be a little less or more likely to happen if A happens. But somehow B is in some way dependent upon A. So it's different than independent events, which completely are unrelated to each other and do not affect each other's outcomes whatsoever. So let's get a formula for dependent events. It's a little bit different than the formula for independent events. So for dependent events, to solve for that, the probability of A and B happening, you have to take the probability of A and multiply it times the probability of A after B, or B after A, actually. All right, so let's take the example of a joker, for instance. A joker, there are two jokers in a deck. Now, sometimes you play certain games with them and certain games without them. Let's take a joker. If you have a deck of cards and you pick a joker out of the card, but you do not put the joker back. If you remember from the example of Kiera fishing, Kiera would catch the fish, but she would put the fish back. But Bryan would catch the fish, and he would keep the fish in his bucket. So Bryan's was a dependent event, and Kiera's was independent. So what if we pick a joker out of the cards, and then we wanted to pick another joker out? Well, picking the first joker actually affects the likelihood of picking the second joker because we've changed the number of cards in the deck and we've changed the number of jokers. So the probability of a joker, it's getting a little crazy here. Sometimes they do that. Multiplied times the probability of a joker after, and this is the key, after a joker is chosen. So let's think of this in terms of numbers, shall we? So the probability of a joker being chosen out of a deck, there are two jokers in 54 cards. The 54 cards in the deck, 52 plus the two jokers. So the possibility of choosing one would be 2 out of 54. Or let's just go ahead and simplify that down to 1 out of 27. So the chance of picking the first joker is 1 out of 27. That's rather low likelihood. But then things change a little bit because now there's only one joker left. But how many cards are there? Well, there aren't 54 cards anymore. There are only 53 cards. So you see, it's just like when Bryan's fishing and he catches a perch and then he keeps it. And it then affects the likelihood of catching the bluegill next. So now there's only a 1 out of 53 chance, because there's 53 cards, and it can't be simplified any further down than that, 1 out of 53 of picking the second joker. So we multiply those two together, and we get a really big fraction. 1 out of 1,431 chance of picking a joker and then picking the other joker out of the same deck without replacing the original joker. And that equals out to 0.0007. All right, or that's 0.0%, 0.07%, 0.07%. I would say that's very low, wouldn't you? And I think that's just basic logical reasoning that is very, very low. How about if we have a bag of chips, and these chips, not potato chips, but like poker chips, and the chips are labeled 1 through 6. And we're picking chips out of the bag randomly by not looking at them. So our second example, that was the joker was our first example. Our second example being the bag of chips. So what if we wanted to pick an even one and then an odd one? All right. So the odd one would have to be chosen after the even one is chosen. So we have a bag of chips. And in that bag of chips, we got the 1, the 2, the 3, the 4, the 5, and the 6. They're all labeled by numbers. And we're looking for the likelihood of the even. So the probability of the even multiplied times the probability of the odd after the even has been chosen. So let's think about this. First of all, the probability of an even number. Even number would be 2, 4, and 6. So that would be 3 out of 6 would be the probability of the even, or 1 out of 2. We can leave it as 3 out of 6 right now if we want. Now we've chosen a chip out of the bag, and if we've chosen a chip out of the bag, there's one less chip in the bag, so the denominator has changed to 5. There's only 5 chips left in the bag. And if we've picked an even one out of there, then we are left with a 3 out of 5 chance for the odd ones after the even has been chosen. So if we take and multiply those two together, we get 9 out of 30. That's the same as saying 3 out of 10, or 0.3, or 30% chance of that happening. All right. So there's a 30% chance of getting an even and then picking another one out that is odd after you've chosen an even. So an even one and then an odd one. One event did affect the outcome of the second event. It did because it changed the numbers of chips in the bag. All right, and our third example will also be the bag of chips, but this time, for example 3, we want a chip that is less than 3. All right, so less than 3, and one that is greater than 3. All right, so to do this, and this is without replacing, so we pick the one that is less than 3 out, and then pick one that's greater than 3. Notice, equal, not in there. So for a chip that is less than 3, remember, here are the chips. They have 1, 2, 3, 4, 5, and 6. Less than 3. Well, there's 2 of them in there that are less than 3. 2 out of 6. 2 out of 6, or 1 out of 3, are less than 3. That's the probability. We multiply that times the ones that are greater than 3, but, we've already chosen one out that is less than 3. So that changes the denominator to 5, because there's only 5 chips left in the bag. And greater than 3 would be 4, 5, and 6. So 3 out of 5. And we multiply those together, we get 6 out of 30. And 6 out of 30 is 1 out of 5. All right. So 1 divided by 5 is 20% chance of that happening. All right. So notice that we have a little bit different type of problem with this than the independent events. The dependent events, the one outcome affects the other one, and the independent events, the one outcome and the two outcomes have nothing to do with each other. So in all three of these events examples that I gave you, the independent, or they were all dependent events. One event affected the other one. All right. So with activity 2, it's going to be very similar to what we did with activity 1, but of course we have bag of chips, and we didn't have that in activity 1, and we also have the cards, which we didn't have in activity 1. So let me take a few minutes just to show you again how to use the CodeApp application. So go ahead and go to the probability activities link on the website, and we will look through this together for a few moments. So here we are back on the website for the probability learning activities. And again, we are going to be looking at the card shuffler as well as the chip picker. So let's take a look at the card shuffler for just a moment. Most of this you probably are able to figure out on your own at this point. You can actually choose the types of cards that you want. We'll just leave it with the normal ornamental cards. Let's say we are choosing one card from the deck, and we just click go. Well, we got an 8 of clubs. All right, well, let's reset this and choose 2 cards, but we are not going to replace the first card after we've chosen it. That checkbox is really important. So we have an ace of hearts and a 3 of hearts. In this case, there was no possible way for us to get an ace of hearts and a 3 of hearts. I'm sorry, an ace of hearts and another ace of hearts, because we had already pulled out the ace of hearts, and we had that in our hand, and it was not in the deck anymore. So that's really important for this activity, because remember, these are dependent events that we're dealing with. All right, so again, we've got our data table here, and we have graphs that we can make also of this data. So this is for the card shuffler. And for the chip picker, this one is probably our simplest of all the apps that we have. We're going to want to, again, uncheck that box that says with replacement. How many chips are in the bag? Well, we know that we've been dealing with 6 bags, or 6 chips. How many do we want to choose out? Well, you can choose 1 and go. And we got a 3. Or we could choose, we could choose 2 and go. And we could get a 6. So what we'd like you to do for this assignment is it's the same again as activity 1, but we want you to instead be using the data or the app for the cards and the bag of chips. And you'll be collecting empirical or experimental data and then comparing that to the theoretical data that we calculated mathematically in notes to see how the results compare. And again, remember, this ties into lesson 2, which was all about this kind of thing. All right, so best of luck on activity 2. Again, it should take about 15 minutes maximum to go through this. You're just generating some reports of some information. You're going to go ahead and multiply some things together and see what you get. Good luck. Welcome back. Hopefully you learned something today in these lessons and lecture notes and whatnot from Lesson 3 on dependent and independent events. Hopefully you understand the difference between the two. It's very important. It will be very important for you when you make your Carnival Tycoon projects, your games, and you start collecting data on those games. There are two other things that we would like you to do before the end of this lesson today. And the first one is, just like what we do on all of our lessons, we have our reflection questions at the end of the lesson. So this one gets you thinking about somebody who had a terribly unlucky day. His name is Jackson. Of course, it's just all made up, but it contains some really interesting statistics. So Lesson 3 reflections document is found on the lesson plan page for Lesson 3. And then we have some practice problems. Practice problems 1 through 6 for Lesson 3. And they have you calculating some different things about dependent and independent events. And then there is a question 7, and you're going to need to follow your teacher's instructions for question 7. This is called the stare game, and the stare game would take a little bit longer, and it really works out well as a group activity. So if your teacher has you working in small groups to solve this problem, this is a fantastic probability problem that involves some really deep thinking, and if you can figure out the stare game, you are certainly moving in the right direction. So that wraps up Lesson 3 on dependent and independent events. I want to just remind you that we are working towards learning all the things that we need to learn to help us do this Carnival Tycoon project. And in the Carnival Tycoon project, you will be designing a game. And remember, this game needs to be fun, so people will play it. But the game also needs to be a money maker. So you have to figure out a way using probabilities and statistics to ensure that this game will make money for the carnival. The carnival has no interest in games that just basically give money to the contestants or give prizes that are worth more than the carnival can afford. The whole idea of the carnival games is it's a business to make money. Some of us really enjoy playing those games, and others of us who are not very good at them, which is me. We skip them, right? So remember, that's where we're headed, and we're about halfway through the lessons right now, and you have an assessment coming up to see what you have learned from the first few lessons in probability also. All right, best of luck doing the practice problems, and we'll see you for Lesson 4.